Welcome, Eleni.
Hi.
Eleni.
Hi, everyone. Hi.
So test coverage.
Yes.
Big subject.
Yes. One of my favorites.
One of mine too, so I'm very excited about your talk. By the way, how do I say your last name?
It's Fragkiadaki.
Eleni, everybody.
Hi, everyone. I'm Eleni. I'm going to be talking about test coverage today, and I'll share some of the things I've learned while I was doing a deep dive on how Go test coverage actually works. So if we start with what is actually test coverage, when we say test coverage, we mean how much of our code gets executed when we are actually running our test suite. So if we get a number back, which is what we usually get when we run our test coverage statistics, and it tells us that 80% of our test is covered, it means that 80% of our statements actually got executed while we were running our tests. I've put a source down there, which is like from the blog, from the Go blog. If you haven't read it, I definitely recommend reading it. It's one of the best blogs I've read about coverage, and it covers a lot of the stuff that we are going to go over today. So really, really interesting blog post. If you like to follow along, I've put together some examples that we're going to go through in the presentation. Everything is already on GitHub. You can get it from the QR code or directly from the link there. You don't need to. We are going to go through all of the examples as we go. But if you fancy like following along while we're talking, this is where you're going to find the code. Cool. So let's start with test coverage. Our first example is going to be mod 1. It is a very simple module. It has two packages in it. It has a package called calculator with a calculator.go and a test file. It has a package called size with the measurements and measurements_test. If we have a look at the code very briefly, this is what calculator actually looks like. It has a struct. It's never used in any of the examples, but it exists there. And it also has three functions. Sum adds to numbers, multiply multiplies to numbers, and abs, which gives us the absolute number for the integer that we pass in as a parameter. The calculator test actually defines a few test cases with what comes in the test case, what is the expected output. There are three cases that we are testing. They are all about the same function, which is the sum function, and they are testing that we are just running the code, and the sum is producing what we expect it to produce in three different test cases. Pretty simple code. Next one, measurements.go. It only has one function in it. It's a size function. It gets an integer, and based on how big or small we consider that integer to be, it returns a string. So it's going to tell us that something is huge if it is between 100 and 1,000. If it is above 1,000, it's going to tell us that it's enormous. Pretty simple test case for this one as well. We have the measurements_test, gets a number, two test cases, one is a negative number, one is a small number, and we are expecting that to be run and return successfully when we are executing our tests. Cool. So this is the example that we're going to use, the first one, and this is how we run our tests. Go test --count = 1, /..., to get a list of all the packages that we have in the directory. It runs the tests. It tells us that it found two packages, calculator and size. All good so far. All of our tests are passing successfully. We get our timings. So the next question is, how do we now produce our coverage statistics for the packages that we have in module 1? So basically, what is the percentage of the test, what is the percentage of the code that we did actually manage to cover with our tests? And the way to do that is by using Go's cover tool. You can invoke it by adding the --cover parameter when you are writing your tests. So go test --count = 1, --cover, and everything else after that. It's going to do the same thing as before, run the tests, but it's also going to append the coverage percentages for each of the packages. So you can see here that our size package has a 42.9% coverage, whereas our calculator package has a 16.7% coverage. Pretty cool and simple, right? Just by adding --cover, you can clearly see where you have written tests, where you still have a way to go if you like to have increased confidence on your calculator package, for example. Nice. What this doesn't tell us, though, is how our mod 1 is doing with regards to test coverage. So basically, we know how each of the packages are doing, but we don't have an overall number that tells us mod 1 is covered X%, or how much of the statements we have actually verified. Put a star here for later. We are going to come back to this. But for now, let's focus on this number, 16.7%. This is a percentage, which means that if we had 1,000 statements in this package, 167 of them would have actually been executed by our tests. So we need to have a way of actually calculating those numbers, right? How many statements do we have in the calculator package? How do we know which ones got executed by the test that we've written? Which is the next thing that we are going to see. And to begin with, we are going to see how that works manually. So we are going to do it by hand, let's say, just to see how that works. So the first thing that we need to understand is what are code branches in the concept of coverage, though. So in this example, this is the calculator.go. Again, the three functions that we saw, the sum, the multiply, and the absolute. And if I were to ask the question, like, how many code branches do we have here? And if I were to give you three options, you could either say, I have 3, I have 4, or I have 5. Basically, which one would you go for? Like reading at the code, you may say it's 3, because we have 3 functions. You may say it's 4. If you saw that down here, there is an if statement. You could even say that it's 5. And we're going to see which one is the correct one. So definitely a code branch up here. We have a function, a second code branch here, a third one here, like we haven't changed anything yet. But we also have this one, which is an inner code branch, which means that it may get executed or it may not get executed. And we also have this one at the bottom. So basically, with regards to our test coverage, what we have is we actually have 5 code branches in here. And that is the correct answer. So the next thing is, if we understand what the code branches are, the next question is, how many statements do I have? And how many statements with regards to how many of them are going to actually get executed? 3 options again. You could say that we have 5, or 6, or 9, depending on how you're trying to count those statements. And if we see what we have, in the first code branch, we have 1 statement. Second code branch, we actually have 2 statements, because we have an assignment and we have a return statement, so there are 2 things in there. And then finally, we count the last code branch as statement, and we also count 1 statement in each of the code branches that we have at the bottom. So if you thought that 6 is the number, that's the actual number, which is great. So now we know how to count the statements. We now know how to count the code branches by hand. Obviously, we would like to do that a bit more efficiently, so we don't want to be counting by hand. So how does Go do this? And how does Go do this? How does it do it programmatically? 3-step process from the point of view of how Go calculates this. So the first one is Go uses a very interesting way of actually figuring out which statements get executed from the code. It actually takes the source code that you have and it rewrites it in a way that it's going to help it when you provide the dash task cover to calculate what got executed and what didn't get executed. So it actually rewrites the source code. It runs the source code and then it dumps the statistics. So the question is, okay, Go does this. This is amazing. Can we see that? And the answer to that is unfortunately no. Almost. I'm joking. Obviously, if the answer was no, this would have been a very, very short talk. I would be going home now. So we can actually see a lot more of these things, and Go does give us the option to see them. So how does this work? Instead of doing Go test dash task cover, you can do Go tool cover, and you can provide it a Go file. And when you do that, it's actually going to dump on screen how Go rewrites the file and what does it put inside it so that it can calculate the coverage statistics. So if we actually run this command, assume that this is dumped on your terminal, this is what we are going to see. And this is for the calculator.go file that we saw before, right? So most of the code is intact on the left, and we also have a bunch of stuff that are printed on the right, where Go actually creates a struct, which is called cover. You can rename it to whatever you want. And it has 3 fields that help us actually calculate and analyze our code. So if we were to see the first one, The first one is a field called count. It's a list that has 5 numbers in it, and those 5 numbers in that list represent the 5 code branches that we identified when we were doing the manual exercise before. So it creates a list, 5 numbers, 1 number per branch. The second one is a pause field. In that field, what you're going to see is like the line numbers of where does each code branch actually start and end. So the first code branch starts on line 7, it ends on line 9, 11, 14, and so on and so forth. So that's how Go actually understands where does each of the branches sit. And the last thing that it does, it creates a field which is called num statements, which has the counters of how many statements do we actually have within each of the branches. So the first branch, which is the function sum, it has 1 statement. The second branch, which is function multiply, it has 2 statements, and so on and so forth, for all of the statements that exist in the code. What else does it add? If you have a look on the left, you're going to see that in each of the branches that we identified, Go adds this Go cover struct.count with the number of the branch, and it actually sets a value to 1. So this is how it will know that if we enter that code branch through a test, that value gets set, and that's how Go understands that that branch would actually got executed, and it's going to calculate it against our code coverage. It's a pretty cool way of doing it, by the way. Cool. Now Go is going to go off. It's going to compile and run the tests. This is a part that we need to trust Go that it's actually going to do. And then the step 3 is us viewing the statistics that it dumps on the screen. So how do we do that? Once we run the tests, we have the option of providing another parameter on the command line, which is called cover profile. And we can give it a file name so that Go can actually dump the statistics in that file. So when you do that, you don't need to specify the -cover anymore because that gets set automatically. And I'm only running this now for the calculator package so that we can see it on screen. And what it is going to do is once you run it, you're going to see the results. Again, 16.7% of the statements got covered, and 1 more file got generated. So you're going to see this coverage.out file that Go generated. Good idea to add that in your git ignores if you are running your tests so that you don't commit them. So what does that file actually look like? If you do a less or cut or whatever, you see the contents of this file, you're going to see that it has the first line, which is mode set. Sorry, another star here. We will come back to this again. And then it has lines that identify the branches that you have in the code. So basically, you will see 1 line for each code branch that exists in calculator.go. And at the end of each line, you are going to see 2 numbers. The first number actually represents the number of statements within that code branch, and the second number represents whether that got executed whilst you were running your tests. So if we look at the numbers and you start adding up the numbers on the left, you're going to see that we have 6 statements in calculator.go. 1 of them got actually executed whilst we were running the tests. So our test coverage, therefore, is 16.7%, and this is what we got back from the cover tool. So this is how Go actually calculates this, and this is how we can see it. Now, this is pretty cool. We saw that Go has a tool that we can use to generate the coverage statistics. We saw how it modifies the source code, and we are actually able to see that. We saw how to calculate code branches, number of statements. We saw what the coverage profile does, and we also calculate the coverage statistics ourselves, so we can verify the results if we ever needed to. But we left a couple of stars along the way. So if we wanted to go back to star number 1, and star number 1 was actually, this is really cool. How can we see it at the module level? Like, we can see it on the package level, but how can we see it at the module level? Someone might think, okay, we have 2 packages. One is covered 16.7%, the other one is covered 42.9%. Can we just not add those 2 up, divide by 2, and get the coverage for the module? Unfortunately, this doesn't work. And the reason it doesn't work is because your packages are very rarely that balanced. Like, for this to actually be working correctly, they would need to have exactly the same code branches, exactly the same number of statements, nothing different between them. 2 of them, nothing different in the tests. So if you have a case where one package has 20 lines and the other one has 3,000 lines, and they are both covered by 10%, that doesn't mean that the code coverage is going to add up to this number. So basically, this is mathematically not correct. So this is not what we would like to do. So what do we do? One of the things that we can do is we can actually make use of the coverage.out file and start calculating the things ourselves, because now we know how Go does it, how it works. We run it, we generate the coverage.out file, and then we can use a little bit of Linux magic on the command line to actually do some calculations, and we can actually see how this works. So if we were to break it down, we run everything as we did before. We generate the coverage file. We actually use an awk program. Awk is a command line program that you can install on your Linux or Mac, and it allows you to do processing of text. It has a beginning, which signifies the beginning of the program. What it does is it defines two accumulators, so cov and stat. Cov is the covered statements, and stat is the actual total number of statements that you have in that file. And then at the end is going to calculate the percentage and print it on screen. And the magic happens actually in the middle, where it is going through all the lines on the coverage.out file, and it's calculating what the sums need to be. So if we were to understand how that works, back to our coverage.out file, the first thing that happens on the highlighted line at the top is it says if parameter 3 is not empty, and we kind of need that because the first line in the file is the mod set that only has 2 parameters. We don't want to include that, so we exclude that by saying if it's not empty, then calculate. If it's empty, don't calculate. And we can see that down here, where parameters 1, 2, and 3 are actually the numbers that we're after. So simple calculations, always add the statements, but only count them as covered if the second number in the line is actually set to 1. And if you run this, you will see the output, which it adds on your screen this total coverage line at the bottom, which says, based on the statements you have and how many were covered, you have a 30.77% coverage of your module overall, which is great success, right? We've managed to be able to calculate this. We used our coverage.out file. We got the module statistics out. Or maybe not. So there's something here that we don't know yet. And what we don't know, we're going to see with the second module, which has an additional package, which is called age. In the age package, we only have one file, years.go, and that's it. Years.go, it has only one function. It calculates the years since a particular number that we assume it's actually a year. And it does some calculations around if it is a negative year, if it is in the future, do some erroring. Otherwise, just calculate the number of years and return. So basically, we have added lines of code in our module right now. We go back to this. We know how to do this. We run it again. We get this output now. And this is an interesting output, because the first thing that we're going to notice is that it does recognize that we added a new package, obviously. It says no tests in this package. And what we notice here is that nothing has changed with our calculation. So basically, we added lines of code. We didn't actually test them, and the coverage didn't go down because the values are not there in the coverage.out file. So something here doesn't add up, right? Let's try something else. Let's add a years_test file, completely empty. There are no tests in there, but there is a file there named years_test. And let's run things again. If you do run the things again, you are going to see that things in the output have changed slightly. And what has changed is we have actually gotten now a test coverage percentage of 0 for our age package. And this is because we just added that file. So by adding that file, basically, Go, instead of just telling us that there are no tests in that package, it has actually calculated those lines as not being covered by any tests. So this is a nice little thing to know. And we can see actually that now that that has happened, our coverage.out file contains those lines, and the coverage is actually 0%. Sorry, not 0%. It's actually gone down from 30.77 to 21.05. Great success, right? Or maybe not. At this point, we are not sure, if I add another file in the age package, and that file has no test, is that going to be counted now? So let's test it. Let's add one more file, months.go. Similar sort of logic with the year since, like it's trying to calculate the months since a particular year and month. Some errors happening there, and then it returns a value. And we are interested now in this one. So basically, what's going to happen? Is it going to actually calculate those lines as statements or not? And the good news is that yes, it is. So basically, so long as you have at least one underscore test file in your package, Go is going to traverse that directory, and it is going to add those statements in your coverage.out file. So if you wanted to do calculations, this will actually work, which is great. Cool. Let's go even further. Like, what happens if we have not just a module with packages, but each of the packages actually has sub-packages as well? So module 5 gives you the size. Inside the size, we added the surface. The surface is like very, very simple. Just one function calculates the square. And we also have a test here that does some calculation about if I give you the number 5, I'm expecting to get back the number 25. What's going to happen now? Again, with our script, we generate our coverage.out file. We try to see what happens in the coverage.out statistics. We see the output, great. We see that the surface sub-package is actually included. We can see that it's actually got 100% coverage. Now, this is great success on its own. Like, we have a package in there that has 100% coverage. And we also see that something has changed with the total, which is, again, great. So we added lines, we added tests. The number got affected somehow. So we know that something happened in the coverage.out file. But then, great success. We are feeling happy now. Or maybe not. I don't know if you've noticed in this case, we added the surface package inside size, and surface got actually calculated correctly to 100%. But now we are back where we were before, where we have something that is nested, and it's not updating the parent, basically. So in this case, we still get the 42.9% for the size. We don't get any sort of like update because we've added a package in there. Another star. So we'll come back to this star as well. But it's good to know that this is happening, like we went back to the same case where we were before. Another thing that I wanted to bring up that I came across as well is what happens when we have a package that actually uses or has inside it Go-generated files. So I've added a new package in this module, which is called Painkiller. It has a pill.go, which we're going to talk about in a bit, and it also has an empty underscore test file because we know now that we just, by default, we should always be having something like that in there. So in the pill.go, the thing that we see is that we have a new type defined. This is called pill. This is basically from the Go generate package example that Go has. So it's pretty standard. If you look at the example, you will be able to find it. So what it does, defines the type struct, which is integer, and it just has a list of values, basically, which are integer values. And what we are using is a utility that Go has, which is called stringer, that allows you to, when you have an integer type, it allows you to actually print strings instead of the numbers for the type. And the important thing here is that you can actually use that with the Go generate tool. So you can have Go run the command generate with the stringer on this type, and it's going to produce code for us. Like, it's going to template code for us that we don't have to write, which is amazing. And this is what this code looks like. So if you haven't seen Go generated code before, usually it has a line at the top that says this is an auto-generated file, and it's usually followed by a do not edit, because even if you try to edit, next time you run Go generate, that file is going to be overridden, so all your changes will go away. So we get this file. It has some definitions at the top, and it also has a function, which is interesting, because we saw that functions actually do count as statements, and they do count as code branches, right? So this is pretty simple function. It returns a few things. It returns us the string. And now the question is, what will happen if we run our code coverage, like little script here? The answer is it is going to find the new package. It is going to calculate the coverage statistics for that package. And because the generated Go file exists in the package at the time where we actually run the script, it is going to count those statements against our code coverage for the code that we have for our module, right? And we can see that here. Our coverage went down because it thinks that we added code that we haven't actually tested, so it's only natural that our coverage is going to go down. So there is a question here. If you do want to use your coverage statistics, what should you do with your auto-generated code? And that's a good question. Like, you could choose to ignore auto-generated code, right? It's not code that you have written. It's not necessarily code that you want to write. That may already be covered by something else. It's good to know that Go is going to pick up on these things if they are in those directories. If you run the tests and that is not there, probably you may not get successful tests depending on what you're testing. But it's interesting to think about, should we include that or not? Now, another example. Module number 7, it's simplified now. We're going all the way back. We have an age and a car. And inside the car, we have a use.go file. And that use.go file basically accepts a list of cars. Cars are very simple. They just have a manufactured year, nothing else. And we have a function that, given a list of cars, it's going to tell us what their average age is. We've already built a function that actually calculates that, and we are using it in this function. So basically, we are saying, from within the use.go file, we are saying, use the age.years since to calculate how many years since the manufactured day of this car, and produce an average. And we also have a test for this. We are giving it a list of 3 cars, 2000, 2001, 2002, and we are expecting that the average age is going to come back as 20 years. Pretty old cars. So we run this again, and what we get back is this result, basically. And what does this mean? It tells us that we have 2 packages again, age and car, 0% coverage on the age, and 85.7% coverage on the car. So it gives us an overall of 25% coverage for the module 1, based on what we said so far, right? Is this what you would expect? Some may say yes, some may say no. It really depends on what we are after in this case. But why do I say depends? If I go back to the previous slide, basically, in here, we are using this function, and this function does exist within module 7. And we do have a test that actually covers that function indirectly, right? We are not testing the function itself, but we are testing that the average age that we are calculating for the cars does actually return the correct result, which means that indirectly we have tested that the average, like the years since, does actually work, kind of like we would expect. So this is an indirect thing. When Go runs, and by default when we do the --cover or like --cover profile, it calculates the statistics, it calculates the coverage, only looking at the test from within the package itself. So that's why age comes back here with 0%, and that's why car comes back as 85.7. So when we calculate it, we are only calculating what I'm going to say from now on as like unit coverage for the packages themselves. It doesn't care if you are indirectly testing something else at all. There is a way to actually do that, and you can provide another parameter on the command line that it's called the cover pkg, and you can actually say go test --count equals 1, and then cover pkg equals /.. which is going to expand to all the packages that you have, and we can still generate the coverage.out file as we did before. So what this will do is it will run as before, it will generate stuff, and now we're going to get back a completely different result for the percentages. So the age still comes back as 0%, and the car comes back as 41.7% in dot/dot. Now, this is a bit odd, right? This has changed as well, but we will see why that happens. What does this mean, though? What does it mean 41%? Why did it get down from 85%? If nothing else, we were expecting to increase the coverage of the age package, not to decrease the coverage of the car package by what we did. Okay, this is weird. So let's deep dive on what does the coverage profile look like once we have run this command. Imagine all of this in a single dump. It's not enough for the screen, so I've split it into two. But what we are going to see is that the coverage profile actually runs the statistics for twice from the perspective of each of the packages that we have. So from the perspective of the age package, this is all the code that we have. And the age package doesn't actually test anything else. Actually doesn't test anything. And that's why everything is set to 0. And we can see that here. When it runs the code from the perspective of the car package, though, this looks different. We know that the car package has statements. We know that it has a test, so we can see the ones that are actually set there. And it also has set some of the statements as being executed from the age package. So from the perspective of the car package now, it has covered 41 point something of the code, right? So here, if we look at the packages themselves, like the unit coverage that I was saying before, we get 0%, 85.7, and the final number 25. If we look at it from, does this package actually interact with other packages, we get these numbers now, which make more sense. Like 0% of the code is covered by age, 41.7% of the entire code is covered by car, and we can actually calculate that ourselves by looking at the coverage file. We have 24 statements, 10 got executed, 41.7%. Now, this is a bit suspicious, though. Like, is that the actual coverage of the module, or is that just the coverage of the car? Which is not very clear in this example. So let's do another example. Same module as before, age, car, and size. And what we are trying to figure out is like what the percentages actually mean, right? We run it just from the perspective of each package itself, and we see these numbers, 0, 85.7, 42.9, 29 as the overall number. And if we look at how the packages interact with themselves, now the numbers have changed as well. So age is still 0%. The car is gone down, so 32.3 of the total statements inside mod 8 are actually tested by car, and the size only tests 9.7% of the overall statements in module 8. Cool. So this is what we see. So we have a total of 31 statements in module 8. 10 were executed when we ran the tests in car. 3 were executed when we ran the tests in size. And that actually brings the overall coverage for our module to 41.9%. And why is that? Because from the 31 statements that we have in the module itself, we know that from one package or another, we had 13 statements that got executed. And this is basically what I would describe as like the integration coverage that spans across all of the packages that we have inside our module. It's a bit different than what we had before. So what to do with unit and integration testing? Like, it really depends on what you are after. If you are after like just the unit coverage from within the packages that you are testing, then you just do --cover and you get those percentages. If you are also interested, if you have complicated modules that have packages and sub-packages that call into one another, and you want to have a sense of how much of my overall module is actually tested by any test, regardless of where it sits within my module, then you can have a look at the integration like coverage by providing the cover_pkg // ... basically. Or you may be interested in both, which is very valid as well. And you can generate two metrics, one for the unit and one for the integration, like test coverage for your modules. Are there any other ways to see the results? So far, we've just focused on how do we do this on the command line, how do we actually run it and see with the awk script how we can parse the coverage.out file. Are there any other ways to do this? And the good news is there are. And the cover tool itself provides another way that you can see the results that is a bit more visual. So you can do go tool cover, and you can provide the HTML parameter with a coverage.out file. So if you have run this, you've generated your coverage profile, you can trigger an HTML view. And this view will have a drop-down, one option for each of the files that you have in your packages. And up here, it's going to tell you as well what was the percentage of that file that got covered based on what you gave it with the coverage.out file. Anything that is gray, I don't know if you can see it, but there are some gray lines up there. It means that it doesn't count against code coverage, so we don't mind. And then red means nothing executed those statements. If we look at the years.go, again, we see the lines that don't get covered and the lines that didn't execute at all. The Go tool is actually clever enough that regardless of whether you give it a coverage profile that is generated by cover profile, or you give it the coverage profile that has the cover PKG with all of your packages, like regardless of whether you give it like a unit or an integration thing, it will correctly decouple the lines and it will correctly count all the statements. So this is an example of the unit test run of the code coverage that gives us 0% for the years. And this is when I give it the coverage profile that is from the integration run. So basically, it does recognize correctly that some of the statements got executed. And you can see that here. Nice. Another way that you can see this, if you're using an IDE, it's very likely that your IDE already provides that as an option. So if you're using Golang, for example, you can right-click on a module, you can tell it to run with coverage, and you can tell it which module to run, and it will give you an output that looks like this, where you can see each of the modules, and you can see the percentages executed for each of the packages as well. And this one is driven from the unit test. So basically, it will tell you that age was covered 0%, car was covered 100%, and you can see the overall level of the module as well. Now back to star number 2. We had left some stars around the place. So the star number 2 was looking at the mode that we saw as the first line in the coverage.out file. And we said we'll talk about it later. So Golang has has different ways of running the coverage. Apart from looking at like the unit test or the integration test, it also gives us the option to run in different modes. And looking into this one, this is a calculator.go. Again, we only tested the sum function. This is the function that we tested. And on the right, you can see that we had 3 test cases. But when we looked at the output of the coverage profile, we only see that that got executed. We don't see any information about like how many times, like how many cases did we examine. So the Go cover tool actually has different modes. By default, it's going to go with set. Set is Boolean. Was it executed? Yes, no. So it's a 1 or 0 always. But you can change that by doing -cover mode, and you can set the cover mode to count. And if you do that, it is going to change what it outputs. So you can see here it said mode now is count. And instead of, this is very out of focus, but instead of going 1 and 0, 1 and 1, so one statement executed, it goes 1, 3, which means one statement executed 3 times because we covered it with 3 test cases. And why does it do that? Because it has a different view in the HTML output that it can show you more green or less green, depending on how many test cases you have covering a particular piece of code, basically. Cool. So in summary, if you are going to look at the cover tool, just be aware that if there are no test files in the directory, The Go cover tool is not going to traverse that, so it's not going to show you coverage statistics for that. Go doesn't calculate nested values, so when it calculates the coverage percentage, is purely on the basis of that level in the hierarchy, so basically only the Go files included in the directory. It doesn't calculate aggregate statistics for modules even. And what it does do, it can output the code for you to see, and it can output the coverage profile, and you can work with the coverage profile however you want. Like you may want to parse it, read the results, and calculate values for yourself. If you try to do the total percentage from the command line, there are limitations to that, and we saw some of them. It only can go one level, so it can aggregate up to the module, but if you have nested sub-packages, it can't do that. So in these cases where you want to actually work with the coverage percentages, I would recommend like writing a script that actually does correct parsing. And if you do a script, you can programmatically detect if you have directories that have no test files. You can programmatically detect if you have auto-generated code, and you can make a call whether you want to include it or not. And you can also aggregate all the way up to the module or all the way up to parent packages and so on. And then good to know that you can do unit and integration coverage statistics, but we just need to be aware like what the numbers mean when you actually see them on the command line. Nice. So that was me and test coverage and Go. Thank you. Cool. So I can ask if anybody has any questions.
Yes, thank you. Okay, any questions for Eleni? Yes.
Hello, a fantastic talk. That's really great. Thank you. Bit of if you're doing a test using sort of a BDD given when then, I mean, you tend to have your kind of given at the beginning where given a customer, you'd add a customer. Do you know if it's possible to get the coverage of just kind of the when part? So kind of almost exclude some, but only keep another bit? Or have you seen anything that would maybe indicate that it's some way possible? Or
to be honest, I'm trying to think how that would translate in the coverage.out file.
Yeah.
And it's a bit hard to think how that would translate unless you could identify the branches and exclude them or include them by yourself.
Yeah.
I haven't tested it though, so I'm going to say it may be possible. I can't think of a way right now of how it would work.
Yeah, I just wondered whether you'd seen anything on your, on your journey through that package. But that was really great. Thank you. Thank you very much.
Any other questions for Eleni there? You know, if you'd asked me, could you do a talk for an hour on code coverage, I would have thought that's impossible. But what a great job. That was so thorough, and there's so much there to think about. It's great. Any other questions? If not, we'll let Eleni go on her merry way. Thank you so much, Eleni. That was great. Eleni, everybody.
Thank you.